Hi everyone, I hope you guys are doing good. Well, in this video, I'm going to teach you how to code for the flip-flop. So let us go ahead and then start coding with the design. As usual, module and then the flip-flop, name of the module. We have to list down the port, clock, reset, D and Q. So these are the signals in the D flip-flop. Now, instead of writing D and Q, let me use some meaningful words, okay, like data input, okay, and instead of Q, I'm going to write down data output, okay. So these are the name change which I've made for our clear understanding. So let us declare the input and output signals, clock, reset, and then similarly input. Let's take 8-bit 7 down to 0 for data in, and for output register same thing, 8-bit, I'm going to use that one, and then data out. Okay, this is the declaration of input and output ports. Now we are going to use procedural block, so always at positive edge of clock. So whenever it is in the positive edge of clock, begin. So condition is like if reset is high, that means if reset is 1, begin, and we have to make data out is equal to 0. Okay, whenever reset is high, data out must be 0, and if the reset is made to low, that is 0, then else data out is directly assigned to the data in. Okay, so data in, that is the input signal which we are going to generate through by the help of test bench. So here we can say like the generated data for data in is passed to the data out. Okay, we can say it like that. Whatever values is there, whatever values are generated by data in, that will be given to the directly, it will be given to the data out. So this is the design part of the D flip-flop. Let's go ahead and write down the code for the test bench. Module test bench and module. Now the input that is declared in the design will be declared as register in the test bench. Reg clock reset, reg 7 down to 0, that is 8-bit for data in, and then the output that is declared in the design will be declared as wire in the test bench. So wire 7 down to 0, and we have to give data out. After that, we have to instantiate the design. Okay, so let's write down D flip-flop, that is DFF. We have to write down this line. Okay, so let me go ahead. D flip-flop design under test, then clock reset, and then data in, data out. Okay, most of the videos I've used for instantiation name, I'm using this DUT, that is design under test, but for this video I'm going to change it, like I can use any name, INST. Okay, instance. Okay, so that is the name I'm giving for the instantiation. Now for initializing the clock, we have to begin with initial begin end, and then we have to give clock is equal to 0, and then forever hash 5 nanosecond clock is equal to inverse or negation of clock. So this line of code will help us to generate the clock pulse. Okay, for 5 nanosecond it will be 0, and for 5 nanosecond it will be high, that is 1. Like that, the clock will keep on repeating. Now initial begin end, so we are going to give reset is equal to high, and for 5 nanosecond we're going to make the reset is high. Okay, see, whenever reset is high, this condition will work. Okay, during reset is high, data out will be 0, no values will be there. But after 5 nanosecond we are making reset is equal to 0. So during this condition, this statement is going to work. Okay, whatever data is there in the data in, that will be given to the data out in the output. So let us go ahead. Now let us give, say, like I want to repeat data in 5 transactions, so let me give repeat 5. Okay, and then so at every, since the condition is at every post edge of the clock, right? So I'm going to use here at the red post edge of clock, begin, end. So at every positive edge of the clock, it is going to generate data in, is going to generate some random values. So that is data in equal to $random. We are going to give another hash, let's say 150 nanosecond. After 150 nanosecond, let us give $finish to end the simulation. Okay, so that is the end of the instantiation and clock generation, and then are providing the random signal for the data in. Now let us also give one more code for viewing the waveforms. See, in order to view the waveforms, we have to give this code $dump file, and then let's give this, let's say test.bcd, and then $dump varies. Let's give 1. Okay, so we want to check the waveform as well as we want to see the values, the 5 random values, right? So we have to use this code. Okay, and then whenever you use this code, make sure that you have to check the EP waveform after run. Okay, in order to see the waveform, we have to check this one, this option. So after this, we have to select the tools. Let's go and select Synopsys. So the code is done, test bench is done, and then even the design is over. So let's go and run the simulation. So this is the signal we got for the D flip-flop. So if you see the clock, for 0 to 5 nanosecond, the clock is low, and then from 5 to 10 nanosecond, the clock is high. So the clock will keep on toggling like that. Okay, and then if you see the reset, for 0 to 5 nanosecond, the reset is high, but after 5 nanosecond, the reset goes to low, that is 0. So in the input, that is data in and data out, if you see here, when the reset is high, there is no value. Okay, they have not generated any values. But after this, once the reset is made low, in the next positive edge of the clock, we can see D in is generated a random value, that is 24, and similarly D out is also getting 24 values, like that. In the next positive edge of the cycle, we are getting 81, and similarly in the D out we are getting 81. So we have repeated this transaction for 5 times. So there is 5 values, 5 signals are there. Okay, and then whatever the input is given, whatever the input has generated the random values, the same value is getting in the output. So this is the working of D flip-flop. I hope you guys understood, and thanks for watching.